Hi there. In this video we're going to take a look at the tangent function. And as a bit of a warm-up, we're going to look at graphing one cycle of a sinusoid. Now a sinusoid is a sine graph or a cosine graph. So we've got these four different sine functions and we've got four different cosine functions. We're first going to revise just what the format and the parameters a and b mean to each graph. If a is positive, the blue sine wave starts at a midpoint or a 0 and goes up to a maximum, down to a midpoint, down to a minimum, and back up to a 0. Meanwhile, the cosine shape starts at a maximum, and it's the same waveform, but it's been translated back a quarter of a revolution. The coefficient a here, and when we take the absolute value of it, that gives us the amplitude, which is the distance from max to mid, or from mid to minimum. Now, if the little a value is negative, we vertically reflect these original graphs. So the sine wave goes first down to a minimum instead of up to a maximum. Meanwhile, the cosine graph starts at a minimum and increases first instead of starting at a maximum and decreasing when a was 0. The second parameter is b, which is a horizontal multiplier, and so the b affects the period, which is kind of given by this horizontal window, the base of this rectangle. And so the period of a normal cosine or sine graph is 2 pi. That means that it takes 0 to 2 pi radians, or one revolution, or one circle of 360 degrees to complete one cycle. But then if this is a factor of b, then we would be able to fit b cycles from a 0 to 2 pi angle. In other words, 2 pi divided by b would be the angle that it takes to complete one cycle. So I'm going to pause the video and have you try these sine equation graphs and then compare with the answers that are coming up. Okay, here are the graphs. First of all, you can take screenshots or have a quick look at the values for a and b for each of the functions. And because of this watermark here, I'm just going to keep scrolling up for the graph of part D. So you can kind of take a screenshot here so that you can see the value of the graphs of each of these functions a little bit better. Okay, so remember there are the values for a and b for each function, and there are the graphs. Okay, we've got similar questions for cosine. We've got 4 cosine graphs. This one is meant to be a cosine, and you can take a look at the values of a, b, at the amplitude and the period for each one. And I will just scroll up so that you can see the graphs without any distraction. So pause the video, make sure you can do those graphs on your own, and we're going to build on this to come up with the tangent function. So when we're looking at the tangent function, we want to be able to evaluate the tangent of any angle. Now we recall that the tangent is the opposite over the adjacent, and as we've been doing for standard position angles, in other words, angles that start being measured on the positive side of the x-axis and either go counterclockwise for the positive direction or clockwise for the negative direction, we can spiral our angle around. We will have a terminal arm, and then we indicate the direction of rotation with an arrow against the terminal arm. So we could end up having an angle that lands in quadrant 1, 2, 3, or 4. Or the angle theta might not even land in a quadrant. It might lie on an axis, 0 degrees, 90 degrees, 180 degrees, 270, etc. So we're going to figure out how to work out the tangent of any of those angles. We're also going to come up with the graph of the basic tangent function and talk about the properties of the tangent function like the period. So going back to our basic definition of opposite over adjacent, we're going to upgrade opposite to y and adjacent to x. And so we are first going to figure out the sine of the tangent of theta depending on which quadrant the angle theta lives in. So let's take a look at the xy axis, or the xy plane, and we notice that in quadrant 1, x is positive and y is positive. This is a Roman numeral 1 for quadrant, so I'll just make it a little bit clearer. Quadrant 1, x is positive and y is positive. So tangent of the angle is going to be positive for y divided by positive for x, which is positive overall. We can also see that in quadrant 3, we're going left and down, so x is negative and y is negative. So in this case, tangent of the angle in quadrant 3 I could put a subscript down here to show that the angle lives in quadrant 1, and a subscript of Roman numeral 3 here to show the angle lives in quadrant number 3. By the definition, tangent is the y over the x, so negative divided by negative, and that final result is also positive. So we see that tangent is going to be positive in quadrants 1 or 2 because the sine of x and y are the same, either both positive or both negative. Meanwhile, in quadrant 2, the x-coordinate, because we're going to the left, is negative, and going up, y is positive. And so the tangent of any angle that lives in quadrant 2 is going to be the y divided by the x, so positive divided by negative will be negative overall. That's because the x and the y coordinates have signs that are opposites, and so dividing a positive by a negative gives you a negative. Meanwhile, in quadrant number 4, we're going to the right, so x is positive, but we're going down, so y is negative. And tangent for any theta 4 angle in quadrant 4 will be the y divided by the x by the upgraded definition, and so negative divided by positive is negative. So we see that the tangent of any angle in quadrant 2 or 4 will be negative. So the justification of our response is really just going back from the definition of tangent plus our pre-existing knowledge about the signs of x and y in each quadrant. So we might summarize this to indicate that tangent is positive in quadrant 1 and quadrant 3. We've seen this before in talking about our basic trigonometry tools, so this is something that we need to know cold. It's essentially a deconstructed unit circle. So we're first of all going to remember our upgraded definitions for cosine, sine, and tangent. Cosine was adjacent over hypotenuse, which is now the x-coordinate over the radius of a circle in the xy plane. The sine of the angle is the opposite, or the y-coordinate, divided by the hypotenuse, or the radius. And tangent is opposite over hypotenuse, which is y divided by x. So with these three definitions, we can come up with the cosine, sine, or tangent for any angle. So let's draw our three reference triangles. Try to make them look realistic, so we want a reference angle of 30 degrees. Label the right angle and the 30 degrees. You could also put the radian measure in here, pi by 6, because it's good to practice. Then we want to draw an isosceles triangle, so really try to get that line to have a slope of 1. We're rising and running as a staircase where the steps are the same height and width. And so we've got 45 degrees, or in radians, that would be pi by 4 radians. Now we're taking this first triangle and we're rotating it so it's taller than it is wide. And in here the reference angle is 60 degrees. Now reference angles are always measured from the horizontal because that's how we measure angles in standard position. And so we want to make sure that even though there's a 60-degree angle up here, we don't want to measure from the vertical for standard position. So we're going to rewrite the angle down here so that we measure from horizontal, so that we're always thinking about measuring from the x-axis in standard position. So this angle of 60 degrees is the same as pi by 3 radians. Now you can scale these triangles so that they have any hypotenuse or radius length that you like. I prefer to use a hypotenuse of 2 because then I don't have to introduce any other fractions. We can easily remember how to label the lengths of these triangles. We've solved for them before using isosceles triangles and Pythagorean theorem. But for now, if we just remember quickly how to do it, we count to 4. We take the square root of each number because when we solve for a length of a right triangle and we use Pythagorean theorem, we end up having to take square roots. And we can simplify the square root of 4, which is 2, and 2 is the largest of these lengths, which is opposite the largest angle. So we've used up the 2. We can also simplify 1, which is the smallest side, so it goes opposite the smallest angle, so I'm going to put the 1 opposite the 30 degrees. The square root of 2 is the next smallest side, which goes opposite the next smallest angle, and the square root of 3 is the next smallest side, or second largest side, which goes opposite the second largest angle. So we should be able to sketch those and label those triangles neatly and clearly in about 10 or 15 seconds. Now we want to talk about the quadrant signs, and we know that in quadrant number 1 we have positive for x and positive for y. That means that every fraction here will be positive. So cosine, sine, and tangent of angles will all be positive. So I'm going to represent an A here to say that all three of these trig functions are positive. It's worthwhile to note that the radius is a distance, because a radius is a distance of a circle, and therefore the distance is always going to be positive. So in order for cosine to be positive, we just need to focus on the sine of x. We know that x is going to be positive to the right of the y-axis, and therefore we're going to have another positive cosine expression in quadrant number 4, because x is positive even though y is negative. Similarly, y is positive anytime the graph lies above the x-axis, because y is positive when we go up. And therefore in quadrant 1 or in quadrant 2, the y-coordinates are both positive. And in quadrant 3, both the x and the y-coordinates are negative. So we knew that tangent is positive in quadrant 1 or quadrant 3, so I'm going to put a t here for tangent. In quadrant 2, x is negative, and so negative over positive radius is negative for cosine. But the sine of the angle is the y-coordinate over the radius. Positive over positive is positive. So I'm going to represent an S here to show that sine is positive in quadrant number 2. Tangent is positive in quadrant number 2, rather quadrant number 3. All trig functions are positive in quadrant number 1, and in quadrant number 4, because the x-coordinate is positive, positive over positive means cosine is positive in quadrant number 4. So I'm just going to tidy up. I'm just going to erase this here and just rewrite my definition. And I'm going to erase this little plus sign because by default, these letters A, S, T, and C represent which trig functions are positive in these quadrants. We sometimes refer to this as the CAST rule, C-A-S-T, or all students take calculus. These are just memory aids. The real reason comes back to the sign of x and y in each quadrant in conjunction with these definitions. The last thing I want to do is talk about angles that do not live in a quadrant. In other words, angles that do not live inside a triangle and therefore do not have reference angles. These are the angles that lie on the axes, and for that I'm going to consider a circle. Now we could talk about a circle of radius 1 and be very, very specific, but the radius of the circle could be anything. So if we talk about a general radius, we could say that the radius is equal to r. And so if the radius is r, we're going to go r spaces to the right, and we're not going to go up or down. So the coordinates here would be r, 0. If we go to the top point, and this corresponds with angles, so 0 degrees, 90 degrees, 180 degrees, 270 degrees, etc. So at 90 degrees, we're not going right or left, so the x-coordinate is 0, and we're going up however much the radius is. So the coordinates of that point are 0, r. For the point to the leftmost on the circle, we're going left, and so the x-coordinate is negative however many spaces. Well, that number of spaces is the radius, which is called r. And we are not going up or down, so the y-coordinate is 0. And lastly, at the bottom point, we're not going right or left, so x is equal to 0, but we are going down, so y is negative, and we are going down the amount of spaces of r. So these are going to form the x and the y coordinates that we need with the same radius of r to work out the sine, cosine, and tangent of the angles that lie on the axes instead of in the quadrants. So these are our complete set of tools that we need, and if we put them all together and reflected these triangles into different quadrants, we would get the unit circle. So I like to think of this as a deconstructed unit circle. And I prefer to think of this because I don't need to go all the way around to come up with all the different points and all the different angles in each of the different quadrants. It's a lot faster to write these things down, and it helps me to understand how the unit circle is constructed. So now we're going to use these tools to work out the tangent of the following angles. The first thing I'd like to do in each case is to work out the reference angle and the quadrant. Now to work out the reference angle, you really want to imagine a picture and sketch the angle in standard position. Reference angles are always measured to the nearest x-axis. So in this case, the nearest x-axis is 0 degrees, so the reference angle is going to be 30 degrees. In other words, it is its own reference angle. And furthermore, the quadrant that we are in is quadrant number 1. So we go back to our trig tools, and we look in quadrant 1 and we see that tangent is positive. So this ratio is going to be a positive answer. I call this a ratio because tangent of an angle is a fraction or a ratio. Each of these is a fraction or a ratio. And in fact, the word fraction contains the word ratio in it. So these are trig functions or trig fractions or trig ratios. Okay, we know that for an angle like 30 degrees, which is in quadrant 1, the tangent of it will be positive, and then we go to the reference triangle and we work out the opposite over adjacent, or the y over x. And so we're going to get that the tangent of 30 degrees is 1 over the square root of 3. Now sometimes we like to rationalize our numbers, which means we multiply by 1 in a form that gets rid of the radical in the denominator. We multiply our fractions straight across, and we get the square root of 3 divided by 3. So we could leave this as 1 over root 3, but it's kind of common not to have an irrational or square root number in the bottom. So we might leave this as root 3 divided by 3. Now in the next case, the angle is 150 degrees, which lies over here. And we measure the difference between 150 degrees and the nearest x-axis angle, which is 80 degrees. And so our reference angle lies in between here, and the difference is 30 degrees. So we actually see that these two angles of 30 and 150 have the same reference angle, which means they have the same reference triangle. The difference is 150 degrees lies in quadrant number 2. So now we just need to figure out, do we have a positive or a negative, the answer from part A. We know part A has 1 over root 3, and in quadrant number 2, the y is positive over the x is negative, and in other words, tangent will be negative. And that's what this summarizes. This just says the sine function will be positive here, but not the cosine or the tangent. So we know to put a negative for the ratio, and then root 3 over 3 for the number part. We do the same over here for 210. We see that 210 lies down in quadrant number 3, and the difference between that terminal arm and the nearest x-axis is the reference angle. So again, we have a reference angle of 30 degrees, but we are now in quadrant 3. So we go and look at our trig tools. In quadrant 3, y is negative and x is negative. So the tangent is going to be positive, which is what this t summarizes. So we're going to have a positive 1 over root 3, or a positive root 3 over 3. And then the last angle is 330 degrees, which lives over here. Now remember, we're measuring standard position, so this is the measurement of the 330 degree angle. But we are interested in the reference angle, which is to the nearest x-axis angle. So if this is 330 degrees, we don't want to measure to 0 degrees. We measure to the coterminal angle of 360, and we get a reference angle of 30 degrees. 30 degrees in quadrant 4, so our answer will either be positive or negative depending on the quadrant, and the same fraction. In quadrant 4, y is negative and x is positive, so the tangent of a quadrant 4 angle will be negative overall, and it will be negative 1 over root 3. Of course, we can rationalize that and leave it as negative root 3 over 3. So we're going to do the same thing for question 6. Here, this should be part A. And we're going to come up with the reference angle in radians because the angle is given in radians. And we're going to come up with the quadrant for each one. So I encourage you to pause the video and try this on your own, and then you can take a look at the answers. So I'm going to prepare to sketch the angles in standard position. And I see that pi by 4 radians lives here. And measuring to the nearest x-axis gives me a reference angle of pi by 4. Pi by 4 is the same as 45 degrees, so if we look back at our triangle, the opposite over the adjacent is root 2 over root 2, and something divided by itself is equal to 1. Furthermore, in quadrant 1, y divided by x will be positive, so all trig functions are positive in quadrant 1, and the answer is positive 1. Now you don't have to put the plus sign here. I'm doing it just for emphasis to help us remember that we did indeed work out the sign. 3 pi by 4 is an angle that lives over here, and in fact if we had our reference triangle, we would just be taking that triangle and reflecting it over into quadrant 1. From quadrant 1 into quadrant 3. So if this angle is 3 pi by 4, This angle here is pi radians, but I like to get common denominators for adding and subtracting and comparing, so I'm going to multiply by 1 in the form of 4 over 4. So 4 pi divided by 4 is this angle, and the difference between them is pi by 4. So we have the same reference angle of pi by 4. This time we are in quadrant number 2. And we know in quadrant 2, if we just draw our cast memory tool, in quadrant number 2, sine is positive, which means that tangent is not. And so we end up getting negative 1. Again, the special triangle that we're working with is the 45-degree or pi by 4 reference triangle, and the dimensions for the height and the base are the same, and the hypotenuse is 2. So root 2 over root 2 is equal to 1. In quadrant number 3, which is where 5 pi by 4 lives, we see that we have a reference angle, or a difference between these two angles of pi by 4 again. And so we're really going to work out the tangent of pi by 4, the reference angle, and we are going to adjust the sign to plus or minus depending on quadrant 3. Well, the reason why tangent is positive in quadrant 3 is because in quadrant 3, both y and x are negative, and negative divided by negative gives us a positive for tangent. Furthermore, we have root 2 divided by root 2, and we get an answer here of positive 1. And lastly, into quadrant 4, we get the 7 pi by 4 angle. Again, that's going all the way around to 7 pi by 4, but then our reference angle here gets measured to the nearest x-axis. But we actually have to loop all the way around, and so this coterminal angle to this line, to that direction pointing east, would be a 2 pi angle. But just like we did with pi, we have to get a common denominator. So 2 pi over 1 is the same as 8 pi over 4. When we subtract these two angles, we get our same reference angle of pi by 4. And so pi by 4 in quadrant number 4 is either going to be positive or negative 1. In quadrant 4, x is positive but y is negative, so y divided by x will be negative overall, and the amount will be root 2 over root 2, which is 1. So this is how we're using our trig tools in a deconstructive way to come up with the tangent of all the different angles. In the next cases, this is part A, we are not going to have a reference angle and we are not going to have a quadrant because these angles lie on the axes. So let's just label these axis angles as 0 degrees, pi by 2 radians, pi radians, which is 180 degrees, and 270 degrees. So here we need to consider a circle so that we can easily come up with the coordinates of the points on the axes. Now in general, if we have a radius that's any letter, or any value I should say, that radius could be r. Now we could substitute the radius with 1 or 2 or 3, but any positive number will do. But in general, if the radius is r, the coordinates of this point will be r comma 0. This point will be located at 0 comma positive r. We're going to the left, so x will be negative r, and y is not moving up or down, so y is 0. And then lastly, we have 0 comma negative r. So we just look at the coordinates of each of these points in order to figure out the tangent by its definition. So let's just remind ourselves of the definition for tangent. Tangent of the angle used to be opposite over adjacent, but we've upgraded that to give us y over x. And so for the tangent of 0 degrees, we put our pencil on the 0 degree angle, and we take the y coordinate divided by the x coordinate. So that will be 0 divided by r. At pi by 2, we take the y divided by the x, and we get r divided by 0. At pi radians, or 180 degrees, we take y divided by x every single time, and we get 0 divided by negative r. And at 270 degrees, y divided by x is going to be negative r divided by 0. Now we want to simplify some of these. So imagine that you have 0 divided by non-zero, which is what we have in the first case. If you have 0 pizza and you have 5 friends, each friend gets no pizza. So 0 divided by non-zero is equal to 0. The reciprocal of that fraction, however, non-zero divided by 0, is a different story. What we're doing is reciprocating these fractions, or flipping them upside down, And if we consider any other pairs of numbers that we flip upside down, like 1 over 2, which is 0.5, and 2 over 1, which is 2, or 1 over 10, which is 0.1, and 10 over 1, which is 10, or 1 over 100, which is 0.01, versus 100 over 1, which is 100. So what we see here is that flipping the fractions makes the numbers go in opposite directions. So as the answer gets closer to 0, the bigger its reciprocal gets. Or the bigger a number is, the smaller or closer to 0 its reciprocal gets. So reciprocal means to flip fractions upside down. So if we flip this fraction upside down, we get non-zero over 0. So these fractions are reciprocals, which means that the answer of the reciprocals, 0 and whatever this is, should go in opposite directions. Since these numbers have gotten very small and are getting closer to 0, here is 0, their reciprocals are getting very large or closer to infinity. So the value of non-zero over 0 is going to be plus or minus infinity, and we can call this infinite in particular, or in general, we might refer to this as undefined. Now, a lot of people refer to it as undefined, but actually it's better to say this is an infinite kind of undefined number. Anyway, I'm happy for you to put plus or minus infinity, or undefined, or infinite. I think plus or minus infinity is kind of cute looking and it's kind of compact, so that's what I'm going to do. Here we have r, which is a non-zero radius distance divided by 0, and non-zero divided by 0 is plus or minus infinity. Or you might see it very often written as undefined. The next case, we have 0 divided by a non-zero number, which is equal to 0. And then we have a non-zero number divided by 0, which is plus or minus infinity, or undefined. So this is a good place to leave off. We should now be able to evaluate the sine, the cosine, and the tangent for any angle in standard position using these trig tools in exercise number 4. So make sure that you have these trig tools in exercise number 4 memorized, that you can recreate them really quickly, and that you can use them for evaluating the cosine, the sine, or the tangent of any angle. That's all for now.